Analysis model. Particle in simple harmonic motion. In this session, we will explore the fundamental principles of simple harmonic motion. Our outline includes the mathematical representation of this motion and the key physical parameters such as amplitude, frequency, and phase. We will examine the specific relationships between period and frequency, and then derive expressions for velocity and acceleration. Finally, we will discuss how initial conditions, like position and velocity at time zero, determine the phase constant, allowing us to fully describe the system. Simple harmonic motion occurs when a particle experiences a restoring force that is directly proportional to the negative of its displacement from an equilibrium position. Mathematically, this force equals negative k times x. By applying Newton's second law, we can describe this motion using a second-order differential equation, where the second derivative of position with respect to time equals negative k divided by m times the position, x. To simplify this, we define the square of the angular frequency, denoted as omega squared, to be equal to the ratio of the force constant k to the mass, m. It is important to note that the acceleration in this type of motion is not constant. It changes continuously as the particle moves. To find the position of the particle as a function of time, we look for a mathematical solution to our differential equation. Since the second derivative of the function must be proportional to the negative of the function itself, trigonometric functions are the ideal fit. The standard solution is written as position x of t equals the amplitude a multiplied by the cosine of the quantity angular frequency, omega times time t plus the phase constant phi. In this expression, the amplitude a represents the maximum displacement from equilibrium, and the angular frequency omega, measured in radians per second, tells us how fast the oscillations occur. The phase constant phi accounts for the starting position and direction of the particle at time zero. The timing of the oscillations is determined by the physical properties of the system. The angular frequency omega is equal to the square root of the force constant k divided by the mass m. From this, we define the period t, which is the time required for one complete cycle. The period equals 2 pi divided by the angular frequency, or 2 pi times the square root of mass, m, divided by the force constant, k. We also define the frequency f as the number of oscillations per unit of time, which is the reciprocal of the period. Therefore, frequency equals 1 divided by 2 pi times the square root of the force constant k divided by the mass, m. Note that these values depend only on the mass and the spring constant, not on the amplitude of the motion. Graphically, simple harmonic motion is represented by a sinusoidal wave. The first graph shows the position x oscillating smoothly between a maximum value of positive a and a minimum value of negative a. This pattern repeats every time the argument of our cosine function increases by 2 pi radians, which corresponds to one full period, t. The second graph illustrates a specific case where the particle starts at its maximum positive displacement at time zero. And in this scenario, the phase constant phi is equal to 0, and the motion is described by a simple cosine function starting at its peak. This visual representation helps us understand how the particle spends its time at different points in its path, momentarily stopping at the turning points before accelerating back toward the center. We can determine the velocity and acceleration of the particle by taking derivatives of the position function. The velocity, v, is the first derivative of position with respect to time, which equals negative omega times the amplitude a times the sine of the quantity omega times t plus phi. The acceleration a is the second derivative, which equals negative omega squared times the amplitude a times the cosine of the quantity omega times t plus phi. From these expressions, we can find the maximum possible values for these quantities. The maximum speed is simply the angular frequency omega times the amplitude, a. Similarly, the maximum magnitude of acceleration is the square of the angular frequency, omega times the amplitude a. It is crucial to understand the phase relationships between position, velocity, and acceleration. These three quantities all oscillate at the same frequency but are shifted in time relative to one another. Velocity is 90 degrees, or pi over 2 radians, out of phase with the position. This means that when the position is at its maximum or minimum, the velocity is zero. Conversely, when the particle passes through the equilibrium point, its speed is at a maximum. Acceleration is 180 degrees, or pi radians, out of phase with the position. Therefore, when the displacement is at its maximum positive value, the acceleration reaches its maximum negative value, always acting as a restoring force toward the center. The specific behavior of an oscillator depends on its initial conditions. The constants for amplitude A and the phase constant phi are determined by the position and velocity of the particle at the start, when time t equals 0. For example, in case 1, if a block is released from rest at a distance a from the center, the phase constant phi must be 0, because the cosine of 0 is 1. In case 2, if the block starts at the equilibrium position x equals 0 while moving to the right, the phase constant phi must be negative pi over 2. This shifts the function so that the particle begins at the origin and moves in the positive direction as time increases. Let us apply these concepts to a practical example involving a block spring system. We have a mass of 200 grams, which is 0.200 kilograms, and a force constant K of 5.00 newtons per meter. The block is pulled 5 centimeters from equilibrium and released from rest. First, we calculate the angular frequency, which is the square root of 5 divided by 0.2, resulting in 5.00 radians per second. The period is then 2 pi divided by 5, which gives us approximately 1.26 seconds. Using our formulas for maximum values, the maximum speed is 5 times 0.05, which is 0.250 meters per second, and the maximum acceleration is 5 squared times 0.05, equaling 1.25 meters per second squared. To summarize, simple harmonic motion is driven by a linear restoring force defined by Hooke's law, where force equals negative k times x. A motion is mathematically described by a cosine function involving amplitude, angular frequency, and a phase constant. A key takeaway is that the period and frequency of the oscillation are determined solely by the mass and the force constant of the spring. They do not change if you increase or decrease the amplitude. Finally, while position, velocity, and acceleration all follow sinusoidal patterns, they are consistently out of phase with each other as the system energy shifts between kinetic and potential forms. To wrap up, consider these review questions to test your understanding. First, think about why we cannot use the standard kinematic equations for constant acceleration that we learned in earlier chapters to describe simple harmonic motion. Recall our discussion on how acceleration changes with position. Second, if we were to double the mass of the object in our block spring system while keeping the spring the same, how exactly would the period of oscillation change? Use the relationship between period, mass, and the force constant to determine the new timing of the cycle.